Welcome to this explainer. Today, we're essentially treating this like an advanced astrophysics seminar, and we're going to take a fascinating journey through the most terrifying yet utterly beautiful cosmic family tree in existence. We are looking at the absolute most extreme objects in the known universe.
Right off the bat, I want you to imagine compressing the entirety of Mount Everest into something the size of a sugar cube. Or picture an object shining brighter than a trillion suns combined. Or a magnetic field so incredibly intense it could literally erase every single credit card on Earth from halfway to the moon. Now, these aren't just wild science fiction concepts. We're talking about very real physical phenomena scattered across our cosmos. Objects that take the fundamental laws of physics and push them to their absolute breaking point.
So, here is the roadmap for our explainer today. 1. Stellar life and death. 2. The extreme neutron family. 3. Gravity's ultimate triumph. 4. The brightest beacons. 5. Listening to space-time. 6. Surviving extreme space. And 7. The greatest unsolved mysteries. Let's dive right in. Section 1. Stellar life and death. The beginning of everything. Every massive star you see shining so peacefully up in the night sky is actually living on borrowed time. Deep inside the core of that star, there is a furious, unyielding battle taking place. It's the outward pressure of nuclear fusion constantly fighting against the crushing, relentless, inward force of its own gravity. It all kicks off with gigantic molecular clouds of hydrogen and dust. Gravity pulls this gas together until the temperatures skyrocket and nuclear fusion finally ignites. But, when that fuel eventually runs out, gravity always wins. The core collapses in less than a single second. The outer layers rebound outward in a magnificent, unimaginably violent shockwave. The result? Nature's absolute greatest explosion, a supernova. For a brief, fleeting period, a single dying star can literally outshine its entire host galaxy.
And here is what I think is the most poetic connection to us as humans. Those catastrophic explosions act as a cosmic forge. The intense heat and pressure create heavy elements like gold, silver, uranium, and platinum. Every single atom of calcium in your bones and every single atom of iron in your blood was forged inside these ancient stars and supernovae. So, in a very literal, purely physical sense, we are made of stardust.
Section 2. The extreme neutron family. Matter pushed to the limit. Moving right into the afterlife of these massive stars, we meet the extreme neutron family. When a star explodes, that collapsed core is left behind. If that leftover core is roughly between 1.4 and 3 solar masses, matter is crushed to its absolute physical limit, and that gives birth to an incredibly dense neutron star. Let's ground these crazy numbers for a second. Our enormous sun is about 1.4 million kilometers across. A neutron star packs more mass than our entire sun into a sphere that is only about 20 kilometers across. It's wild. Just 1 teaspoon of this material would weigh billions of tons. It is essentially a gigantic atomic nucleus hovering in space. The only things that surpass them in extreme density and sheer gravitational power are supermassive black holes, which scale up to millions or even billions of solar masses. Now, let's contrast your standard neutron star with its much more active cousin, the pulsar. Some of these neutron stars are spinning hundreds of times every single second. And as they spin, their magnetic poles blast out intense beams of radiation. If those beams happen to sweep across our line of sight here on Earth, we detect them as perfectly regular, rapid pulses. It's exactly like a cosmic lighthouse rapidly sweeping its beam through the dark. What's truly amazing is that their rotational precision is so flawless, it actually rivals our best laboratory atomic clocks. But wait, it gets crazier. Enter the magnetar, which is an even more extreme variation of a neutron star. While a pulsar is defined by those precise lighthouse beams, a magnetar is defined by pure, raw magnetic power. We're talking about a magnetic field thousands of times stronger than an ordinary pulsar, and sometimes a quadrillion times stronger than Earth's magnetic field. To put that into perspective, if a magnetar were sitting exactly halfway between the Earth and the Moon, its magnetic field is so incredibly strong it would wipe out every single bank card and electronic device on our entire planet. On top of that, their solid crusts occasionally crack under the stress in violent events we call starquakes, which release utterly terrifying bursts of gamma rays. Section 3. Gravity's ultimate triumph. Black holes. Now, if a dying stellar core happens to be exceptionally massive, meaning well beyond that 3 solar mass limit we talked about,
Absolutely nothing. Not even the incredible outward pressure of those crushed neutrons can stop the collapse. At this stage, gravity wins entirely. And the result is the universe's ultimate phantom, the black hole. The event horizon is the boundary of this object. It is the sheer, absolute point of no return. Once you cross that line, gravity becomes so immense that escape is physically impossible. Not even light, which is literally the fastest thing in the universe, can return. And deep down at the very center lies the singularity, an infinitely dense point where our current established laws of physics just completely break down and cease to make any sense. If you were unlucky enough to fall toward one of these stellar mass black holes, you'd be introduced to a terrifying physical reality that astrophysicists actually call spaghettification. Because the gravity scales so extremely as you get closer, the downward pull on your feet would be drastically stronger than the pull on your head. These enormous tidal forces would literally stretch your physical body into a long, incredibly thin stream of subatomic matter long before you ever even reached the singularity. Section 4. The brightest beacons. Quasars and blazars. So we know that nearly every major galaxy hosts a supermassive black hole right at its center, containing millions or billions of times the mass of our sun. Our own Milky Way revolves around one named Sagittarius A star, and these giants essentially dictate galaxy formation and the birth rates of the stars around them. Now, when these supermassive behemoths actively feed on matter, they become quasars. The sheer friction inside their swirling accretion disk heats gas up to such extraordinary temperatures that a single quasar can shine brighter than hundreds of billions of stars combined. But if that quasar happens to launch a massive jet of highly energized particles moving near the speed of light, and that jet happens to be pointed directly at Earth, we call it a blazar. Imagine a terrifying, hyperluminous cosmic blowtorch extending from millions of light years through empty space. That is a blazar. Section 5. Listening to space-time. Gravitational waves. Thankfully for us, we get to observe these extremely dangerous objects safely from Earth using modern scientific technology. For centuries, human astronomy relied entirely on capturing light. But today, we possess the mind-blowing ability to literally listen to the fabric of space-time itself using incredible facilities like LIGO. We do this by detecting gravitational waves. To wrap your head around this, just think of a perfectly still pond. When you drop a stone into that water, ripples spread out in all directions, right? Well, when unimaginable cosmic weights, like two black holes or two neutron stars, collide and merge, they send physical ripples through the actual fabric of space-time itself. Detecting these incredibly faint ripples is an absolute game changer, allowing us to safely study the most violent, cataclysmic collisions hiding in the dark universe. Section 6. Surviving extreme space. What happens if humans approach? Let's play out a scenario. What would happen if hypothetical future human deep space missions placed our astronauts right in the crosshairs of these cosmic monsters? Let's run through a survival checklist. Though, honestly, it's really a literal checklist of doom. Approaching a standard neutron star means facing crushing tidal forces and fatal radiation long before you could ever try to land. Get too near a pulsar and you risk taking a direct hit from those devastating sweeping beams of radiation that would instantly fry any spacecraft. How about a magnetar? Its magnetic field would severely distort your very atoms and instantaneously wipe out all your life support electronics. Approaching a quasar exposes you to sterilizing unimaginable heat from its massive accretion disk, and trying to fly your ship through a blazar jet guarantees extreme, instantaneous particle bombardment. Surviving any of these scenarios is, well, virtually impossible. Section 7. The greatest unsolved mysteries. Having looked closely at all these extreme, deadly phenomena, we really need to zoom back out to the theoretical frontier of astrophysics. Because despite all our incredible technological advancements, the cosmos remains deeply, profoundly mysterious. There are massive questions out there that our current physics simply can't answer. The big one is the information paradox. This is a huge, current scientific debate surrounding the mechanics of the singularity. The fundamental laws of quantum physics explicitly state that information about the universe cannot ever be permanently destroyed. Yet, when matter falls into a black hole, it seems to just vanish entirely, seemingly destroying that information forever. So which core law of physics is wrong? We honestly still don't know. And this paradox opens the door to even wilder theories. Some scientists suspect there could be primordial black holes, tiny ones formed right after the Big Bang, that might actually explain the dark matter holding our galaxies together. Or what about white holes?
This is the exact mathematical opposite of a black hole. It's a theoretical region of spacetime where matter violently exits, but absolutely nothing can ever enter. We've never actually observed one in reality, but the math says they could exist. All of this leads us to the ultimate mind-bending question. Some theories actually suggest that the extreme compression of matter inside a black hole could spark the creation of baby universes. If that's true, could every single black hole be the seed of a brand new cosmos? Could our entire universe, literally everything we know, see, and experience, have emerged from a black hole sitting inside another, much older universe? It's a deeply humbling thought, and it reminds us that every single extreme object we observe out there is an open invitation to continue exploring the greatest frontier of all. So keep looking up and keep questioning.